So this is the material from week 2, and we talked about this a lot. Heat transfer modes, conduction, convection, and radiation, and the types of convection, whether it's forced or natural. And why do we need to know these? Because of two things, mainly because we want to transfer heat from one location to another, and also because we want to know how are we losing heat, where is it going. Again, the first law of thermodynamics is the conservation of energy. We want to know where is it going, and we should account for every amount of heat that we're losing. So somebody said if you have a wood stove or if you have a radiator, who was talking about radiators? Felipe. He was asking me about steam radiators, and somebody said we can put a fan in front of the steam radiators and it will speed up the process. So it's going to get hot, but it's going to take a while for the entire room to be heated. So if you put a fan on it, that will be faster. That's why we have fans on front of those radiators in the hallway. They also have something called a convector. A convector is basically, it looks like a small cabinet with a very elaborate radiator, and there's a fan underneath it that will blow air and speed it up. Usually you'll see those in courtrooms or big lecture halls where there's no space for fakes. You need to put duct, and if you put the radiators on the floor, it's not going to heat properly. So you'll need a convector. They call it convector because it uses forced convection to blow air out. Also, if you buy one of those space heaters, usually it has a small heating element and a fan in front of it to pull the air to speed up the process. We also talked about the difference between a regular oven and a convection oven. So a regular oven uses natural convection. There is no fan in it. The heat will rise and fill the whole oven. Meanwhile, convection oven, it's very quick. What it does is it circulates the air around the cavity of the oven. Even though it's smaller, it heats up quickly. The air fryer, same thing. Very strong heat element, and hot air circulating quickly the food. So heat transfer fluids, you'll see that also in chapter 2 in the book. So these are the mediums, the fluids that we use to transfer heat from the source to where we need the heat. So we have air. That's for forced air system. That's also what we have to circulate around the radiator. And that's what we actually are surrounded with is air. Water, we can use heat transfer fluid like water from the boiler all the way to each room. So water does transfer heat with forced water. Or you can use steam, which is also water. Steam carries more energy in it. It's quick. It moves by itself. It does not require a pump. We can use black oil or antifreeze. That's very important when you are in places where the temperature drops quickly. If you put only water, it will freeze. And to make things a little bit more analytical, you can look at your car system. If you live in New England, you cannot just put regular water in your radiator. It will freeze and it will break your engine and your radiator. So think of the car heating system, which is very similar to what you have in your house. What is your heat source in the car?
Heating coils.
No.
Is it the engine?
Engine.
It is.
The engine generates a lot of heat. We're already burning fuel. Actually, the heat is the only free thing you get from your car. It's free because it's a waste. If you can minimize the amount of heat that comes out of the car or you lose out of it, you'll significantly improve the performance of your engine. What is the engine efficiency? The gasoline combustion engine efficiency.
Awful.
Yeah.
It's like less than 35%.
Yeah, 35%. We're talking about efficiency, which is changing the energy in the fuel into mechanical power. That's really little. So the rest of it is mostly heat that you only use in the winter. In the summer, it becomes a menace where you have to keep cooling the engine, otherwise it will overheat.
What's the movie Back to the Future, where like they use like garbage and stuff to like fuel a car?
Yeah, that's science fiction though, but it's possible.
That's the flux capacitor.
In theory, yeah. So You can use garbage to make heat. I don't know, in a car.
Mr. Khan?
Yeah.
I think they use oil now on the radiant floor.
They can use oil, synthetic oil. There are some kind of synthetic oil you can use.
Just something to heat up the closed loop.
It is heat transfer fluid. You can use oil, synthetic oil mostly, because it does not react with the pipes. And also you have to have some kind of a cord between the pipes, material, and whatever fluid you put into it, otherwise it will rust. Sometimes they use water, because you have a leaky radiator, you keep adding water to it. If the water becomes too much, water will react with the engine and you have a lot of rust coming out. If you drain one of those boilers, usually there's a drain here, so you can change the water, it comes out very rusty. So that's another issue.
That's a bottom blowdown, right?
Yeah, blow down system. Yeah.
I know, so a pump, like, circulates, like, mixtures, like, everything goes through, like, all,
I can't hear you.
the pump goes, like, it pushes, like, all, like, the water, like, fluids and all that stuff, right?
Yeah.
So, like, how is, like, just pump, like, every single minute, or, like, every single second? I don't know, like, I forgot how it works.
I don't understand your question.
Circulator pumping the fluids?
Yeah.
Like, how does it, like, pump it?
It pushes the water around. It adds pressure to the water. It has an impeller in it. The impeller keeps pushing the water forward and it adds pressure to it. When you have pressurized water, it will move. And also with water, there is displacement. You cannot push water if you don't have something pulled in, right? That's why a lot of pumps need priming. If there is no water in the pipe, the pump is not going to work. And that's the difference between a circulator and a pump. A circulator will circulate water around. The pump will be able to pull water from against gravity. And we'll talk about that as well when we try to select a circulator or a pump for our system. So what about non-fluid transfer, which is not convection, it's conduction? How is that? How does that take place? I mean, just for information, you can have steel rods mesh around the walls and ceilings to conduct heat. That does happen. In a lot of designs in old houses, they will have the wood stove, and they have big rod coming out of it, and it branches, and it will heat the floor. And you can have a radiator, basically rods coming out of the chimney that will conduct heat, so you can dispense it in a bigger space.
Or like heat sinks.
Sort of, yeah. Kind of a network of a metallic part to dispense heat. For example, it just came to me.
Heat sink.
Heat sink, that's something actually pulls in heat in one spot. This is actually, you're not sitting, you're spreading the heat.
I thought that's what a heat sink was. It dispersed it. Or does it work the other way around?
The other way around.
Oh, okay.
It's a spot to pull all the heat. If you look at the rear windshield,
Oh, yeah.
and you see that little mesh of wire in it, it's for defogging, that's kind of using solid to heat transfer.
Electric.
Yeah, it's electric, but it's spread out, so it will heat the window evenly, and it will defog your window. So there's the possibility to use stuff like that to dispense heat. Okay, heat loss in a building, we say it's two things: infiltration and transmission. Infiltration is air exchange. You have air coming from the outside to the inside, inside to the outside, and they are at different temperature, which means they will average out. If the air inside is 70 and the temperature outside is 0, what will be the average temperature between 70 and 0? 35, which is the average. So it's going to average out. So we test for that using the blower door test. We are required to have a minimum amount of air exchange, otherwise we'll suffocate. We need some good quality air to breathe. And there is natural loss and there's mechanical. If the house is very airtight or in a place where there's not a lot of wind, probably you have to provide mechanical heat exchange, which is basically a vent or small fan to the outside. The fan will not work very well if there's no opening. Probably you realize that. If you have a fireplace in your house, you turn on the fire, you have to crack a window. Otherwise, where is the air coming from? You can have a lot of back draft, which you don't want. Okay?
What's mechanical infiltration?
Mechanical infiltration when you have a vent
Oh,
with
that.
a fan in it. Transmission is heat transfer through a medium. That's what we do the calculation on. walls, windows, close windows because it's solid, doors, floors, and ceiling. This is all transmission through a medium, through a wall. So it's because we have a solid wall does not mean does not conduct heat. Any question about this? So in the calculation, the infiltration can be calculated using blower door test. For our project, we will just use the infiltration rate given in the book based on the number of walls with openings on it. That's kind of a rough estimate. If you want to be very meticulous about it, you'll have to do a blower door test and see how much this house is infiltrating air. Transmission, we go through the R value or the U factor for each one of those walls, doors, or windows. Question?
This project is kind of like simulating whether a company is doing a commercial or residential. It's not gonna be just up to one person. There's like a finance, they probably determine the price.
Yeah, but usually they send one person to do the measurement and do
Do
the
the whole
calculation.
thing, like this project, is the project kind of signaling how a company would like do it?
They will send somebody to do the calculation. So they will send Joe and he will go and take the measurement, fill in all the sheets and find out the BTUs. And probably you're gonna have to do the layout because you saw the house and took pictures of it. And somebody else will do the sales,
So,
yeah. And probably you might do the installation yourself, at least do a proposed installation. Yeah.
A new apartment complex in Amherst, there was a guy doing every single apartment. And he was looking for people to do full-time work, just that.
Yeah, yeah.
He's gonna give, if they know how to do it from here, if they're from here, he was gonna give them a whole blower door test, all the tools, and send them out.
Yeah, I mean, there's big demand for these kind
Like
of
right
jobs.
now,
And
he
they're kind
wants
of,
somebody now.
yeah. And they're fun if you got the hold of it.
Go for
If you can do it, probably it will take you 2 hours to do the calculation. Not that much, the heat loss, and you will say how much will it cost to heat that house, and probably it's worth a lot of money. I don't know how much you
once you
paid.
get a
but-
spreadsheet going in, you can just.
Yeah, once you understand what's happening,
You can just type in the numbers and you know, okay.
but a lot of people think it's voodoo.
Voodoo?
Yeah, they look at numbers and they're, oh, what's happening? They don't understand what's going behind the walls and what is the calculation behind it. So, again, that's why you're here. So I'm gonna torture you a little bit by doing this calculation. Because if you get the heat load analysis certificate, if you tell somebody you know how to do heat load calculation, they will be very pleased. That will make you very attractive to the employer. Because again, some company will want this person who's willing to do this kind of work and get paid to do it. Because they will say, we size this boiler based on this person's calculation, and he knows what he's doing. And you're gonna provide with what numbers they use. You're not gonna just ballpark and eyeball it. Eyeballing, by the way, is very common. They look at the house, that looks like a 70,000 BTU for me.
That's good.
Everything's 100,000 or more now.
Yeah, see? Which is a lot. That's a lot of heat. You
No.
yeah.
Do you, now, the customer isn't gonna always know exactly what kind of insulation they have in the walls. Do we go by what was code around the time the house was built?
Oh, you mean what's in there?
Yeah.
Sometimes you have to go and test it, look at it, and see what do they have.
Just
And
a small little hole, one
You-
of those viewing things. I have one. I can.
over time, you'll be able to predict what's in the house based on the time when it was built, and you can ask your colleagues.
And even like the window types and all that.
Yeah.
It's like,
You'll develop this experience. Go ahead.
So how long does it take, like from start to finish?
middle
doing
of
those,
last century,
like the
it's not
calculation?
Well, it depends. It depends on how
I know.
available the material is, how you look at it. You have to go and visit. You have to do the measurement. If there's a floor plan, that'll be great. But mostly there is no floor plan. You're gonna go and take measurement. You're gonna have a sketch for the house. You're gonna sketch the floor plan. Look at the wall material. You can dig a hole, as you said, and find what material is there. And you'll be surprised that a lot of walls are completely empty. There's nothing.
Or the insulation does this and
Yeah.
settles.
But is
Yeah.
it gonna take like more than a day?
Yeah, could be 2-3 days. Yeah.
is there any computer program to do this?
Yeah, there is, but the computer doesn't know what actually is happening. So you plug in numbers and walls and it will do it for you. There's a lot of software and apps to do that. But it's really worthwhile to know how is it done. Because the computer cannot account for a wall made out of more than one material. They have some kind of standardized walls. And if you have the Excel sheet going, it's gonna be really easy. You can go to the wall and see what's in there, estimate what is the R value, and just put it in there and do the rest of the calculation. Any questions?
How much in trouble would you be like if you just got like the wrong like BTU?
It's not about being in trouble, it's like not going to be a good fit. And it is within your interest and the state interest to have like the proper amount of heat going on. Otherwise, if you oversize it, as he said, everything is 100,000. Yeah, I guess put more. More than always better because it's going to cycle more and it costs you a lot of money. The problem is when you undersize it,
You're never
that's why
gonna-
people always oversize it.
Yeah.
You're not gonna reach the heat required and people are gonna be upset.
Yeah, you
Or
do
cooling.
15 right off the bat,
Yeah.
plus an extra 15 for every bathroom, right?
Yeah.
15%.
50% of whatever you
Oh, yeah,
calculate.
15, yeah.
Okay, so heat transfer, you need to know the material properties, which we talked about. Where do you find these properties? You can go online, you'll find a lot of websites that have all the material properties. You have your H22 book. There's also the J manual, which I don't know, for some reason they sell it for like $300, even though it's a small book. But it's a book that has all the material property. What are we looking for? The U factor. That's the whole thing. You need to know the heat transfer law. What is that? It's over there. On the board, Q equal A times U times delta T. And design an outdoor temperature. So for heat, we design for the coldest day of the year. And that data is available readily online. And design temperature, how hot do you want it inside? And that's something between 65 to 80. Like 65 is the standard, like the lowest you can go, and 80. So that's the design temperature. Yeah.
So like, when you're doing it, and you're doing the outdoor temp, you're like the temp, like at that time and day?
Yeah. Now you're gonna go. Are you asking about the outdoor temperature?
Yeah.
So you're gonna look for the coldest day of the year. You're not gonna decide for 30 or 40. So you're gonna go look up, for example, Chicopee, coldest day of the year.
0.
It's gonna be 0. Maybe changed by now. This data has been consolidated over the last 10 years because they want to design for the most possible extreme case, where you will be able to heat the house comfortably and avoid the water freezing or the system breaking or whatever. Installation. So we'll talk about the installation, and we did go to that equation that you have in your book on how you calculate the installation required. So we do the calculation. We find that we're losing a lot of heat from the floor or from the roof, like extremely high. For example, if the room is losing around 5,000 BTU from the floor, you gotta do something about it. Or if you're losing 5,000 BTUs from the wall every hour, you gotta do something about it. You're gonna install some insulation. So let's look at this for this example. We did that before, but let's do it again. We did a heat loss calculation. We realized that the room loses 4,000 BTUs per hour. The room has only one wall facing the outside. So we know that we're losing that heat from that wall. Okay? The area of the wall is 8 by 15. The wall U factor obtained from H22 is 0.45. So you look at the wall, it's 0.45.
That's awful.
The inside temperature is kept at 70 degrees, and the outside coldest temperature is 10 degrees. What is the R insulation you need to reduce the heat loss by 50%?
You-
So
Same,
let's look about the equation you have in the
same thing for
back of the book.
increase. Twice that. It'll make that twice as small. So it'd be 22.5. What, 225? Yep, because let's say, wait, 1/45 is, I don't know, but if.
What is the equation?
It's 1/T, right? So if you double
Area times what?
underneath,
Delta T?
it'll cut the U factor in half. When you cut that in half,
120?
you reduce your
It's
total.
the area times
Equation is like
delta T
times
over
delta
the
T.
Q that you need
So
minus R
you
wall.
cut that number in half, you're gonna cut your BTUs in half.
Do we have the area?
Yeah, 120.
Yeah.
Delta T? The Q that we want?
0.45.
So, no, we have 4,000 BTUs, right? One half of that.
2000.
Oh, he's doing like this, okay.
If any of those numbers do not make sense, let me know.
Oh, so then you wanna cut that in half?
Yeah.
So then, yeah, 2,000.
Oh, okay.
This. What is our wall? 1/0.45.
That's our U val.
That because
Yeah, okay, that's
R
gonna be our
equal 1/U. Take it step by step. Get here 3.6, and this is 1/0.45.
2.222.
That's the R value.
1.38.
You're not gonna go and buy 138, you're gonna buy two, 1.5 or something more. But this is the minimum that you have to cut down by 50%. You can go higher, whatever you can find. Any question? Jason, you got it?
Yeah,
If you use the other equation, oh, that's for infiltration, never mind.
What was the last numbers you did?
Why did we cut
3.6?
50%?
Just
2.22
arbitrary.
minus 2.2.
Yeah.
So what does that R value represent per inch?
Insulation,
Per inch?
yeah.
That you
No.
would need by 50%.
That's what is the R value you need to add to that wall?
To reduce the heat loss
Yeah.
by 50%.
Yeah,
So you're gonna cover the wall with insulation that has the R value of at least 1.5.
So if the current R value was,
The current R value is 0.22, 2.22. That's the current R value of the wall. You're gonna add this to it.
okay.
Where did you get the
Yeah, you're gonna add more
3.6?
insulation. 3.6 is this, the result of this number.
Oh, okay. So then it's 3.6 minus the
R
one,
wall.
1/0.45.
Yeah.
So what's the equation where we just double the R value to?
It's the same one.
No, but there was one where we could just
2.22.
take a look at it and say, oh, just cut the U value in half or something like that.
It's the same one.
Or like double it.
Are you wondering why, how come we just didn't double the insulation?
I guess like when we found our U value, why didn't we, so that's our R value now.
Yeah.
Why didn't we just double it? Yeah.
So your
Would we
R
double
val-
it if we were working with 4,000 still? Okay, so we did the same thing basically because you divided it before you put that.
Yeah.
Okay, so it would make sense if you just kept the 4,000 and then just doubled the R value.
Yeah.
Okay.
But however, now 50% is just an arbitrary number because we wanna make it easy.
Yeah.
I'm just trying to get you to follow up the process. How much would that add value to my calculation?
This makes more sense. Yeah.
So let's do this one. I will have you do this one by yourself. Just pause.